We begin our discussion of syntax with a look at the basic words of our language. We then talk about how these words can be combined to form complex expressions called terms. And finally, we talk about how terms can be combined to form sentences. In propositional logic, sentences are constructed from a basic vocabulary of propositional constants. In Hebron logic, there are no propositional constants. Instead, we have object variables and constants. In our examples here, we write both variables and constants as strings of letters, digits, and a few alphanumeric characters, mostly the underscore character. By convention, variables begin with letters from the end of the alphabet. Examples include U, V, W, X, Y, Z. By convention, all constants begin with other letters other than U, V, W, X, Y, Z, or digits. Examples include A, B, C, 1, 2, 3, Comp 225, Barack underscore Obama, and so forth. There are three types of constants in Hebron logic: object constants, function constants, and relation constants. Object constants represent objects. For example, Joe, Stanford, USA, 2,345. Function constants represent functions on objects. For example, mother, father, the age of a person, plus, times, and so forth. Relation constants represent relations on objects. For example, knows and loves. Now, there's no distinction in spelling between object constants, function constants, and relation constants. The type of each such word is determined by its usage, or in some cases, in an explicit specification. As we shall see, function constants and relation constants are used in forming complex expressions by combining them with an appropriate number of arguments. Accordingly, each function constant and relation constant has an associated arity, that is, the number of arguments with which the function constant and relation constant can be combined. Function constant relation constant that can be combined with a single argument is said to be unary. One that can be combined with two arguments is said to be binary. One that can be combined with three arguments is said to be ternary. More generally, a function or relation constant that can be combined with n arguments is said to be n-ary. A signature consists of a non-empty set of object constants, a possibly empty set of function constants, and a non-empty set of relation constants, and an assignment of arities for each of the function constants and relation constants. For example, we might have a signature consisting of the object constants a and b, the unary function constant f, the binary function constant g, the unary relation constant p, and the binary relation constant q. A term is defined to be a variable, an object constant, or a functional term, as we'll define in a minute. Terms typically represent objects that are presumed or hypothesized to exist in the world, and as such they are analogous to noun phrases in natural language. For example, Joe, or the car's left front wheel. A functional term is an expression formed from an n-ary function constant and n terms, enclosed in parentheses and separated by commas. For example, if G is a binary relation constant, and if A and Y are terms, then G of AY is a functional term, as are G of AA and G of YY. Note the functional terms can be nested inside of other functional terms. For example, we can apply the function constant G to the functional term G of AY and the functional term G of YA to form a more complex functional term. There are three types of sentences in Hebron logic. There are relational sentences, which are analogous to propositions in propositional logic. There are logical sentences, which are analogous to the logical sentences of propositional logic. And there are quantified sentences, which express the significance of variables. A relational sentence is an expression formed from an n relation constant and n terms. For example, if q is a relation constant with arity 2, and if a and y are terms, then the expression shown here is a syntactically legal relational sentence. Note that, unlike functional terms, relational sentences may not be nested within other relational sentences. So it would be inappropriate to say q of a and q of ay. Logical sentences in Heilbronn logic are defined the same as logical sentences in propositional logic. There are negations, conjunctions, disjunctions, implications, and equivalences or biconditionals. The syntax is exactly the same, except that the elementary components are relational sentences and equations and so forth, rather than proposition constants. There are two types of quantified sentences: universally quantified sentences and existentially quantified sentences. A universally quantified sentence is used to assert that all objects have a certain property. For example, the expression shown here is a universally quantified sentence asserting that if P holds of an object, then Q holds of that object and itself. The universal quantifier is notated by this upside down A. An existentially quantified sentence is used to assert that there are objects having a certain property. For example, the middle expression here is an existentially quantified sentence asserting that there's an object that satisfies P and, when paired with itself, satisfies Q as well. The existential quantifier is denoted by an E rotated through 180 degrees, as shown here. Note that quantified sentences can be nested within other sentences. For example, in the first sentence here in the bottom, we have a quantified sentence inside of a disjunction. And in the second sentence at the bottom, we have a quantified sentence nested inside of another quantified sentence. As with propositional logic, we can drop unneeded parentheses in Heilbronn logic, relying on precedents to disambiguate the structure of unparenthesized sentences. In Heilbronn logic, the precedence relations of the logical operators are the same as in propositional logic, and quantifiers have higher precedence than logical operators. The examples here show how to parenthesize sentences with both quantifiers and logical operators. The sentences on the right are partially parenthesized versions of the sentences on the left. To be fully parenthesized, we would need to add parentheses around each of the sentences as a whole as well. Notice that in each case, the quantifier applies only to the sentence to its right, even though the other sentence also contains occurrences of the quantified variable. Okay, this exercise tests your grasp of these rules of syntax by asking you to determine whether various expressions are syntactically legal sentences in Heilbronn logic. Before we leave our look at syntax, we need to define some additional useful concepts. An expression in the language of Heilbronn logic is said to be ground if and only if it contains no variables. For example, the sentence P of A is ground, whereas the sentence for all x P of x is not ground because it contains a variable. An occurrence of a variable in a sentence is bound if and only if it appears in the scope of a quantifier of that variable. Otherwise, it's said to be free. For example, x is free and y is bound in the sentence shown here. And finally, we say a sentence is open if and only if it has free variables. Otherwise, it's closed. For example, the first sentence here is open, and the second one is closed.